guys, welcome back to the tetrahedron chemistry classes. So guys, if you can recall in my last lecture of NMR spectroscopy lecture series, I have stopped at this particular point, this particular slide which you can see here. Okay, so if you can recall, this was my last slide, and in this slide I was actually I already explained to you how we can get the NMR signal. So this was your T2 relaxation, right? And as you know, in T2 relaxation your random phase approximation would achieve, right? And here you can see these this is your net magnetization oriented bunch together, right? It is the signal intensity at its maximum after the 90-degree pulse, and when you switched off the instrument at this point, right? So what would happen? The T2 relaxation would occur. However, T1 relaxation would also occur, but I am not going to explain the T1 relaxation as I have already explained, right? Since this T2 relaxation is responsible for giving the NMR signal, so I am explaining this T2 relaxation. So what would happen? The spins which were actually bunched together when we have applied the RF radiation, and when I switched off that RF radiation, then what would happen? Due to this T2 relaxation, these bunched spins now begins to separate, and now they will spin in the XY plane freely, right? And at this point, if you put a coil here in this direction, right? Here, this I have already explained. If you put a coil here, then in this coil there would be a current, and this current would give you actually the EMF, and this EMF is actually your NMR signal. Okay, so this is actually the dephasing which is giving the NMR signal. Now if you can see here, a signal is observed along the x-axis because we have put the coil here, and this signal is called the free induction decay signal. So what is the meaning of the free? Free means your spins are free to rotate in the XY plane. That's why it's free is there, right? Induction, that means the induced current is there for this one. And then decay means when the time passes, your signal will actually die. So here at this point you can see the intensity of the signal is maximum, and it is oscillating in that manner, right? This is time, right? And this is the intensity. When the time passes, actually you can see the signal is actually decaying, and ultimately it will die. And this actually will give you the FID signal. So this was the concept of the NMR signal which we can get in the form of the FID. Now the question comes, how your FID looks like. So again you can see in this particular slide, this is your FID, free induction decay signal, and what I have written here, the composite FID. So what is the meaning of the composite FID? For example, you have this structure. So this is the structure of your phenylacetone, CH2, C double bond O, CH3, right? Say this is the structure. Okay, so when you do the NMR spectroscopy for this one, and say this compound is giving you the FID, that means free induction decay signal, that FID would look like that. So in this FID, you will have the frequency of this one, say I am calling this as nu1, and frequency of these protons which are your CH2 protons, say I am calling it as nu2, and then of course in the phenyl ring you will have the hydrogens attached, 5 hydrogens attached to it. Okay, so of course the nu3 is there. So actually this FID is the combination of these three frequencies, right? So as you know, in your in pulse excitation, what we do generally, we give the short burst energy to the system, and all the nuclei, no matter whether they have the same chemical shift or the different chemical shift, they will excite simultaneously at the same time. And from there actually, since all these would have the different chemical shift due to the different frequency and different relaxation rates or the relaxation times, so when they relax back actually, so they give the individual signals, but in this FID actually all these frequencies are together. So this is your time domain spectrum, because it is dying with the time. It is actually the picture of your FID, and here is the intensity of the signal is maximum, you can see here, and then it is going down. So actually your FID looks like that. This is your FID which contains all the signal. This is just one example. say you may have a bigger molecule. Say for example, if you have any steroid compound, say you have your flavonoids compound, then there may be the possibility of having more than one sets of the hydrogen. So say if the 5 types of hydrogens were there in that particular compound, that means the 5 different frequencies would there. If the 10 different kinds of the hydrogens are there, then 10 frequencies would be there, and that 10 were added together to make this FID. But right now, in case of the phenylacetone, the only 3 frequencies, that mean the set A proton CH3, set B proton CH2, and set 3 the phenyl protons, they are actually adding together to make this FID. Okay, so this was the concept of the FID. Now what we can do with this FID, right? Say this is your picture again, you can see. So say you have your molecule, this phenylacetone, which I have written here, and you are doing the broadband RF pulse. You are giving broadband RF pulse, you know, when we excite or when we actually pass this radiation, typically for the microsecond range. That's why the time duration is very short. That's why it is known as the pulse. And this pulse contains actually the various kinds of the frequencies which are needed to excite the different kinds of the protons. So actually, if this is having the 3 sets, this is the set 1 again, this is set 2, and this one is the set 3. So for excitation of these 3 sets, all the ingredients are there in their short burst RF pulse. Okay, and when you do this, so what would happen? All would excite simultaneously, but as I told you, these will have the different say relaxation rates or the relaxation times. So say this was your alpha state, this was your beta, and this was alpha, this was beta, this was alpha, this was beta, right? So this is just for your explanation. I am showing this, from the background of the NMR spectroscopy, you know that there are number of the nuclei in the higher spin state which are coming from here to here. So excitation is already happened actually, and after excitation, the resultant population I am having here. So this I have already explained to you in my last lecture also. Again, I am giving you the picture. For example, I have alpha state and I have also the beta state, and here say for example I have 1000 nuclei. Then here for example I am having 990 nuclei. And you know, according to the Boltzmann distribution law, we will always have the excess nuclei in the lower spin state, that is in the alpha spin state. So what would happen actually, in the alpha state I was having 1000, okay, and here I'll have 990, and when I pass this RF radiation or RF pulse to this one, so what would happen? Alpha would excite to beta and beta would come back to the alpha. Okay, so 1000 are going up and 990 are coming down. So total I am having the 10 excess nuclei here, 10 excess nuclei. This concept is very, very important, and these 10 excess nuclei will give you the NMR signal. So this was your explanation, but in this diagram I have shown only the one spin. So this excitation has already taken place, and when this spin will fall back from beta to alpha, it will give you the NMR signal, and again when it fall back from beta to alpha, it will give you the NMR signal, and similarly from here it will give you the NMR signal. So 3 different signals will give you will be given by this particular molecule, but in the pulse excitation we'll have this composite FID for this one. So now what we will do to get the spectrum for this one, right? So what we will actually process this FID through the computer, which is equipped with the Fourier transformation. Fourier transformation is a mathematical technique which we generally exploit in the NMR spectroscopy to get the spectrum actually. Okay, so this was the case actually. So these are the 3 different frequencies, and after excitation, if you do the excitation, actually I should have shown this particular slide first to you, right? So this was the situation, and once you do this pulse excitation, you will get this FID. Okay, so this FID you were getting here. So I am removing this one, and when this FID is processed through the computer, then I will get the spectrum of that particular compound. Here you can see this was the new one, this was the new 2, this was the new 3, and you can see here it is a little out of frame. Okay, now it is okay. You can see nu 1, nu 2, nu 3 have the different half-lives. They have the different half-lives due to the different relaxation rates or relaxation times. So they will give the signals at the different chemical shift or the different delta value. Okay, because the relaxations are different for this one. Then you can see after processing that particular FID, we will get this kind of a spectrum for your say this particular phenyl acetone. So I hope this is clear to you. So here you can see the composite FID is transformed into the classical NMR spectrum, and of course this is the classical NMR spectrum which you generally get in the olden days of the NMR spectroscopy. So little I can explain. You can see here, say I am calling this the set A type of the proton. All these protons are of same kind, and this is set B kind of the proton, and this is the set C. So three different sets are there. Definitely we should have three different signals in the NMR spectrum. Of course I am getting the NMR signal here. If it is not clear to you, I can highlight this in that manner. From here you can see this is your first signal, and the chemical shift of this particular signal is 2.0 or 2.1, which I have written. And you can see the three protons are written here. That means this signal is getting, and in this signal, see if you calculate the area under the peak actually. So this thing you have done in your class 8's mathematics, where you have given the graph paper and you have to calculate the peak under that, say your circle, and say area under your say triangle, and all these things, all this stuff you have already done. So this is the spectrum. Now what you can do, if you calculate the area under is this peak. So it is not the height of the peak actually, right? It is the area under the peak. If you calculate the area under the peak, it will give you the value of the 3, right? And it is not necessary it will give you the 3. It can give you the 2.5, it can give you the 2.8, and it can also give you the 3.4. It is up to you, and it is your expertise how you can count these electrons depending upon the structure. However, this thing you will learn only when you solve the various structure, and when you will do the research actually based on this one. So when you do the research on your natural products or any kinds of the compounds, and you solve the spectra of your compounds, then you will learn these things. But right now you can understand in this way. If we calculate the area under the peak, and if it corresponds to the 3, that means the 3 such protons are there, and 2.0 is the chemical shift. Okay, now what you can do, this particular signal belongs to this nuclei. Now coming, you can see here, this is again, if you calculate the area under this particular peak, so this is the peak again, right? Second peak. If you calculate the peak under the area, so it will come 2, and the chemical shift is what? Somewhere around 3.8. You can see here it is 3.8. 3.0, 4.0, in between them you can have the 3.8. So chemical shift is 3.8, and number of protons 2. So of course this particular peak is due to this one. Fine. And finally you can see I am having this signal at 7.1 ppm, and if I calculate the peak under this particular area under this particular peak from here to here, then it will correspond to the 5 protons. So 5 protons means proton 1, proton 2, proton 3, proton 4, and proton 5. 5 hydrogens are here actually, and this particular signal is due to this one. See, however, later I will explain the chemical shift and the general chemical shift of the different functional groups. But right now I am giving you the a key here. Whenever you are finding in your in your MSc courses and in your some competitive examination courses, if you are finding the peak somewhere around at 7.1 ppm, and you are having say 4, 5 or 6 protons, then the benzene is probable. So it is very important to note that the benzene's protons will resonate at 7.0 downfield signal. We can call this as downfield signal. So this was actually the spectrum of phenyl acetone. But nowadays you will not have, or say if you do the NMR spectroscopy for your molecule, then you will not have this problem, this graph type of the problem, right? Now they will give the simple plain paper, and on that particular plain paper you will have your peaks, and integration sign were there actually, and after that integration the number of the protons would be written there. Later in some other class I will show you the original spectrum which we generally have after the NMR spectroscopy, right? I will produce a particular spectrum which actually my own spectra from my some of my published research paper actually. So I hope this is clear to you. Once you get the FID, and then this FID is transformed into the classical spectrum. So this was the concept of your getting your NMR signal, right? T1, T2 relaxation, and then the FID, and you are passing this FID through the NMR, see this Fourier transformation series, right? Using that particular computer, you will have this particular spectrum. So this is the idea how we can get the spectrum in NMR spectroscopy. Okay. See guys, now say I am going to explain the instrumentation of NMR spectroscopy, which is important for your theoretical type of the questions which you generally have in your MSc examinations. I'll not go into the details of the hardware used in the NMR spectroscopy because it is not of much use for you. So, but if you want to learn the details, so you can go through the NPTEL lecture by Professor Hanudatta Attatreya. You can type the NPTEL NMR, so you will have the window will open a playlist of NMR spectroscopy by Hanudatta Attatreya actually. So actually that the professor explained all the things in pretty much detail, but according to me this is not very important for the MSc peoples, right? Or say for your CSIR NET and the GATE examinations. That's why I'm not covering this one. I'll explain only a very short detail of your classical instrumentation. So first I am instrumentation. So first I am taking your classical instrumentation. Why I am calling it as classical instrumentation? Because these type of instrumentations were typically used in 1960 when the early days of NMR were there actually, right? And in this type of instrumentation, actually the field is scanned. Right. So what is the meaning of the field is scanned? You can see here. So this is the rough cross-section diagram of your NMR spectrometer, right? Simplified, it is a 60 megahertz instrument. Okay. And this actually you can find everywhere in your say spectroscopy book. And what is happening here, I am explaining to you. Say these are the magnets which are there in the NMR spectroscopy, and the strength of these magnets is approximately 1.41 Tesla, and there could be the error of plus minus a few ppm. So ppm is actually the parts per million. It is the scale of the NMR spectroscopy, NMR spectrum actually, and this 1.4 Tesla you can easily convert into the megahertz also. So it is actually your homework actually. You can try to convert this Tesla into this megahertz, and you can find whether they are actually corresponding the same thing or not. This is the homework. If you are not finding the result, then you can comment in the comment section. I will provide the explanation in some other video. So right, so this was the magnet actually, North Pole and the South Pole, and this is your NMR tube. So I am not discussing the hardware. I am clearly showing to you the NMR tube. However, this NMR tube will sit into the NMR probe, right? And other coils are what there actually. I'm not going into that much of the detail actually. And you can see here the black part. This black part is actually having what? The sample. Your sample, your molecule, along with some solvents and some internal standard. I will talk about the internal standard also. And you can see this actually your NMR tube is not static at the particular position. It is continuously revolving. And see, this NMR tube actually is nothing but it is a glass tube. It's a glass tube of very small dimension in which you can put your sample. Okay. And it is continuously revolving. Why it is revolving? Because it is necessary that all types of the nuclei, all types of the protons in the sample will experience the same kind of the magnetic field. That's why the sample is continuously revolving. So that say for example, this is your NMR tube. So some molecules will be in the center of this tube and some molecules will be on the walls of the tube, and this technique is very sensitive technique. So there may be a possibility that the molecules at the wall will experience different kind of the magnetic field, and in the center will experience the different kind of the magnetic field. But in NMR spectroscopy, it is essential and it is must that all kind of the nuclei, whether they are present at the wall or in the center, they must actually experience the same kind of the magnetic field. For this, we will generally rotate the sample so that the clear movement of the molecules from here to here takes place, and average magnetic field experienced by all the nuclei would be the same. That's why it is revolving. Okay, and these are the coils through which we will send the NMR RF radiation. So here you can see the RF radiations I have written here, and this is 60 megahertz instruments way back in the 1960, right? And then these radiations are coming from here. Now you can apply all the theories what I have explained in the NMR spectroscopy. You can imagine all the things are happening here. See, all the nuclei were there. Alpha and beta state we have generated by keeping the nuclei in the magnetic field, and when you are passing the radio frequency waves, and these nuclei were also revolving, also rotating. When the frequency of these nuclei, rotating nuclei, matches with the frequency of the radio frequency waves, then there would be the transition from alpha to beta and beta to alpha, right? All this you can imagine, and then you will have your signal somewhere here in the form of the FID, right? So, and then your RF radio frequency detector would be there, which is a receiver. Actually, it will receive the signal, and after amplification and certain things were there actually, though I have not shown here. And finally you will have the recorder. Recorder is nothing but it is a chart paper. Then you will have the NMR spectrum. So this is the old classical instrumentation of the NMR spectrum. So NMR spectroscopy. Now what is the problem with that NMR instrumentation? The problem is just like that. You can see what I have written here. See, first you can see here this particular one. To cause absorption of the incoming 60 megahertz, the magnetic field strength B0 must be increased to a different value for each type of the proton. So what is the meaning of that? So again I am taking the same example. Say this is your methyl, and for this methyl actually the excitation would occur. That means your resonance would occur, say somewhere around at 59.999700 megahertz. And for this methynyl proton, the value is given here 59.999820. And for this phenyl protons, the value is 59.999995 megahertz. So here typically the field is scanned. So what is the meaning of the field is scanned? See, what can happen? You can convert this, say for first I am taking this one, 59.999700. You can convert this megahertz into the Tesla actually. It will give you the value of the Tesla. So what you will do? You will fix the magnetic field at magnetic field to that particular value, which is actually corresponding to this in the Tesla. Okay. And once you fix the value, and you will scan your system. You know, when you do the scanning for this one, and so you have to wait for a while, and then you are having say signal corresponding to this one. After some times you will not observe any signal or any enhancement in the signal. That means it is sure that now we have the sufficient intensity of the signal at this magnetic field strength. Now you will increase the magnetic field. Now the second highest value is 59.999820. Now again you can convert this into the Tesla. This is for your explanation. However, the instrument will do this all things automatically, or it is a duty of the technician which will perform the experiment actually. Now again you will come to that particular magnetic field, and again you do the scanning, and for this scanning if you continue the scanning, then you will get the signal for this one. And after that you can see the 59.999995. And again you will see, you can see the magnetic field related to this one, and you will fix the value of the magnetic field here, and again you can see you will do the scanning, and then you will get the signal. Okay, so you can see you will waste a little of time to get this peak, then to get this peak, then to get this peak. So this is the meaning of the field scan. That's why I have written here to cause the absorption. That means the absorption of the radio frequency waves and the resonance, right, of incoming 60 megahertz instrument. The magnetic field strength B0 must be increased to a different value for each type of the proton. This is the meaning of that. Now you can clearly see this can take several minutes to plot a single NMR spectrum. And this is the problem. You cannot waste time in your project or in your research, right? So these days actually the instrumentation is quite advanced, and you may have the advanced instruments, NMR spectrometer, right? FT NMR instruments, which take actually few seconds to plot a spectrum. So this was the concept of your classical wave, right? And difference are very, very small. You can see the difference are very, very small in the range of the parts per million. So you can conclude from here also that NMR scale is in the parts per million, which actually I have shown you here also. So this scale is in the parts per million. This ppm, however, it is not very clear. It is written here ppm, parts per million. Why? Because the difference in there, you can see the frequency is very, very less. So this is how you can get the NMR spectrum by using that continuous wave NMR spectrometer. So why it is calling the continuous wave NMR spectroscopy, where I have written CW classical. Okay, so I have missed that particular slide, but you know this is called actually CW NMR. So CW NMR means continuous wave NMR spectroscopy. That means you will continuously radiate, or you will continuously pass this 60 megahertz radio frequency wave to the system, but you will not give the short burst or the pulse here. The pulse you will give in the FT NMR, but here you will do this kind of thing, right? So this is the typically the field is scanned, and after scanning, so this is the picture you can see, right? So it is little out of the frame here. In the classical NMR spectrum experiment, the instrument scans from the low field to the high field. So what is the meaning of the low field? You can see here. So this is actually your low field, the low value of the magnetic field, and this is high field, high value of the magnetic field. So whatever the signal which will appear at the low field are called the downfield signals, and which appears from actually the higher field, they are called the upfield signals. So however, I will explain this upfield and the downfield signals later on when I'll solve the spectrum based on the NMR spectroscopy. And you will scan actually this whole magnetic field, and then you will get your NMR chart. Okay, so this is how you can understand the things actually. And of course, after that you can see here, after that you will have this NMR spectrum, right? And this NMR spectrum, if you compare with the earlier one actually, where I have right, this is the spectrum for the first one, you can see, which you were getting through the FT NMR. And this one for phenylacetone, you can see this is phenylacetone spectrum, and you are getting this one. So the two spectrum actually are same. There is no difference in the spectrum for a particular compound if you use the CW instrument or your FT NMR. So but nowadays you can see actually we use the instrument with very high frequency. Say if you are doing the natural product research or the synthesis, you are interested in the small molecules, so your 6 megahertz instrument is 6 megahertz machine is quite enough, 5 to 600. But if you do the proteins or some say in the protein or in the polymers, then you may require 1 gigahertz machine also. But for small molecules, for natural product chemist or for the synthetic chemist, up to 500 to 600 megahertz machine is quite enough. But initially in the CW case, we have used the 60 megahertz. And if you can recall the sensitivity of the NMR spectrum, NMR spectroscopy, which I have explained in my earlier lecture, if you increase the magnetic field, then you may actually have the better sensitivity, because on increasing the magnetic field, we have the higher excess population in the alpha spin state, which I have explained in my earlier lecture. So guys, if you are new here and watching the lecture for the first time and you haven't seen the previous lecture, I am giving you the link in the description. You can go through the lecture series. And moreover, I have also arranged actually the playlist in the tetrahedron chemistry classes, so you can search from there also. So there is no difference in the spectrum. Now the people can ask, if there is no difference in the NMR spectrum of your, say, one we are getting from the CW, that is continuous wave, and second we are getting from actually your say FT NMR. what is the difference between the two, why we are doing these exercises. So one, I already told you, if you increase the magnetic field strength, you will have the better sensitivity, better signal. And second, it will take the very less time. FT NMR will take the very less time, because pulsed excitation would be there, relaxation process and all these things would be occur very quickly. So now we can compare the two techniques, comparison of CW and FT techniques. FT I have already explained to you, right? And just now I have explained your CW also, continuous wave. Now what is the difference between the two techniques, right? So you can see the first one, I can show you here actually. Continuous wave method, the older method, the classical method, the magnetic field is scanned from the low field strength to the high field strength, while a constant beam of radio frequency wave, that is continuous wave, is supplied at a fixed frequency, say 100 megahertz or whatever, right? Using this particular method, it requires several minutes to plot in a spectrum, and this method actually is slow, because you are actually changing the magnetic field again and again, and then you are scanning your system, so it will take the time. So this process is the slow process. And very high noise level. So if you know the little of the electronics, then you should know what is the noise. Noise is unwanted signal. Unwanted signal, right? So this noise should not be. However, every instrument would have the noise. Say you can take the example also, if you are listening the FM and you are not getting the proper signal in some actually out of signal range, so you will have the some disturbing sound in your actually FM radio, and that disturbing sound is actually what? The noise. So every instrument will have the noise. Noise is the unwanted signal which we don't want, and very high noise level would be there in the continuous wave NMR spectrum. Now we can come to this pulsed Fourier transformation, right? FD technique. So it's a newer computer based technique, very fast, because all the different types of the nuclei will excite simultaneously, right? And when the simultaneous excitation is there and you will not scan the field, obviously the method would be the fast. Since the instrument have now this instrument has advancement, so this noise is quite low, right? When the noise is low, then the spectrum would be clean and clear, and you have to interpret your compound very easily. Okay, so what is the advantage of the FT? The most proton relax or the decay from their excited state very quickly within a second, so it will take a very less time. And the whole process actually, the excitation pulse, the data collection, that is the FID, and the transformation this FID into the NMR spectrum, that means through FT, all these process takes a very little time, few seconds. That means you can plot a spectrum for a molecule within a few seconds when compared to your continuous wave NMR method, where you have where you required actually minutes to plot the single spectrum, right? The pulse data collection cycles may be repeated every few seconds. Say for example, if you are getting a signal and you are not actually satisfied with the intensity of the signal, so what you can do, you can go back and you can again repeat all the process for the enhancement of that particular signal. And this enhancement or this repetition of the work of repetition of the cycle can be performed in the very few seconds, right? So many repetitions can be performed in a very short time, leading to the improved signal which I have explained, right? And then you can see here, this is the noise. Say for example, this is your desired signal in which you are interested, okay, and these are the noise, okay. So this is the first case. And in the second case, you can see again what is happening here. If you're adding the second pulse here, you can see here again this is the peak. So by adding the signals from pulses together, the signal strength may be increased. So what will happen? You can see this is a very important point here, which actually I don't want to go into that much of the detail, because those details are not very important for the CSIR net and the gate examinations. When you add these pulses, this is pulse 1, this is pulse 2, and you can add the number of the pulses. So actually the signal strength would actually add it together to enhance the intensity of the signal, but noise actually will not be added to the same extent. However, there is little mathematics involved in explaining this one, but I am not going into the detail of this one. So you can simply remember that if you do the first pulse, second pulse and various pulse, and you can repeat the spectrum, so your signal intensity actually will add it together, and hence the enhancement would occur. However, the noise would not be added to the same extent. This is just for your explanation, and after that you will have this particular signal. So this is the signal enhancement with no noise actually. Right, so this is a very clean spectrum. So this is the instrumentation of the NMR spectroscopy, continuous wave and the pulsed NMR spectrum. I have done this lecture in a very short duration, and I didn't go with the details of these hardware and all these things. And if you want to learn these things, you can go through the NPTEL NMR lecture series by the Professor Hanudatta Attatreya. So that's it for today. In the next class, guys, I'll start the chemical shift and the factors affecting the chemical shift, and then we'll solve the sum of the spectrum based on the proton NMR spectroscopy. Okay. So guys, if you are continuously watching my lecture and you are grasping the things correctly, you are understanding the concepts, right, which I am explaining in my videos, and you haven't subscribed the channel yet, please subscribe the tetrahedron chemistry classes. And if you have subscribed the channel, do share with your friends actually, right? And don't forget to press the bell icon for the latest notification. Thank you very much.